Hello everyone and welcome again, and I hope you all are doing good and keeping track of the lectures and trying to figure out if you have certain problem, so you are free to ask any questions, writing the email and request this live session for that. So now in today's lecture I'm going to discuss the concept of generalized momenta and the cyclic coordinates, and then try to see that the conservation based on this if you have based on the cyclic coordinate and concept of conjugate momenta, the conservation of the linear momentum, angular momentum and energy. So let us try to see that how much I can finish this in this class. So straightforward, starting the concept of generalized momentum is that, so once you have a Lagrangian, so if you can see that uh, when the potential is position dependent only, then I have this delta x dot is delta t by delta xi dot and delta v by delta xi. So this is for free particle. Okay, so then I can have uh, the corresponding momenta concept is there, which is going to be conserved. So in general, how you define the conjugate momenta? So the generalized momenta that is associated with the coordinate, generalized coordinate, is defined as is delta L by delta Qj dot. Okay, so if you have some coordinate q, and then if you take the time derivative of that q, and if your Lagrangian is depending upon, if you have a Lagrangian which depends upon q dot and this t, so if you take the partial derivative of your Lagrangian with respect to the generalized velocity, then that corresponding quantity is known as the generalized momenta. Okay, so notice that this, if q is not a Cartesian coordinate, so this pg does not necessarily have the dimension of a linear momentum. Okay, so because if this q can be anything, because you know that when you write the Lagrangian and you decide what is my generalized coordinate, it could be x, y, z, r, it could be r, it could be theta. Okay, and then what is the term of, what is the dimension of this potential, that you can decide that, because if in the numerator, what you have in the numerator, you have the energy, so that is energy is ml square t minus 2. The dimension of the energy, numerator you have ml square t minus 2. So if the denominator is your length, that is if it is r, so this is, if q is r, so then q dot is, I'm going to have, because you're going to differentiate with respect to time, then the time component is going to be there, so q dot is going to have L by t concept, that is lt minus 1. Okay, this is going to be the velocity. So if in the numerator you're going to have the velocity, so then what you have is ml and t minus 1, mlt minus 1. So this is what this is your linear momenta, because linear momenta p is mv, this is going to be ml t minus 1. But when your denominator is theta, so then pj, this conjugate momenta is not going to have, is your angular momenta, because when you have theta is your q, and then q dot will be going to be theta divided by t. So this is going to have a dimension of t inverse, because theta is not having dimensions, so you're going to have the dimension of t inverse. So what you're going to have is this total ml squared t minus 2, then you have t minus 1 from here in case of theta. So what you're going to have is ml squared t minus 1. So ml squared t minus 1 is the angular momenta, because you see the angular momenta L is rp is r times mv. So this is going to be r l and this m and then lt minus 1. So m l squared t inverse. So this is ml squared t inverse is going to be the angular momenta. Similarly, if your qj is momentum, so if your qj is momentum, then you see the qj, when your qj is momentum, we have to write like if qj is momentum, that is the momentum, linear momentum. When you have linear momentum, this is mv, so you're going to have the dimension mlt minus 1, and then you have q dot, so this is going to have mlt minus 2, mlt minus 1, and then you are differentiating with respect to time, so this is going to have mlt minus 2. Okay, so you're going to have mlt minus 2. So, and then in the numerator what you have, ml square t minus 2. So you have in the ml square t minus 2. This t minus 2 t minus 2 will cancel, m will cancel, and then this l. So you see the pg is now going to have the dimension of the length. So it is not necessary that it depends upon what is the dimension of the q. Then on that basis you're going to decide what is your pj, the quantity which is here in case of is the generalized momenta or the canonical momenta. But this quantity is actually when you differentiate your Lagrangian with respect to the generalized velocity. Okay, so mostly that is going to be generalized canonical momenta or mechanical momenta. You see linear momenta, all sort of thing is without any discrepancies. But the example, if you see the example of the electromagnetic field where your potential was velocity dependent potential. So the catch was here that my potential is only depending on the position coordinate, not the velocity. But if your potential depends upon q and q dot also, that is on generalized velocity, as in case of electromagnetic potential, you have seen that is going to be q phi plus a dot v. That was my electromagnetic potential with a scalar and vector potential when the charge particle is in moving in a free field where electric and magnetic field are present. So my Lagrangian is depending upon the velocity here, r dot here. So because Lagrangian is t minus v contains the velocity. So if I try to find the conjugate momenta, that is a conjugate momenta, that is my p is going to be is delta L by delta q dot. So q dot role play is here is I dot, and this is r dot, because it's going to have the kinetic energy as well as the potential energy. So kinetic energy, I'm going to have velocity, and in the potential I'm also going to have velocity. So normally if the potential is not dependent upon the velocity, then these kind of terms of not going to be appear there, as we have seen. But only this is going to be there, that is mass times velocity is going to be linear momenta. So this is going to be your linear momentum. But since the potential depends upon the velocity, so from there a factor is being added here. This is q times, q is here representing the charge. So it's not the generalized velocity, and this q and this x component of this, and the x because it depends upon this is having ax component, ax, ay, az, and this is going to have component of this x dot, y dot, and z dot. So when you differentiate with respect to I, you're going to have q times ax, because there is a dot product. So this quantity is coming in addition to the linear momenta when your potential is depending on the velocity. Okay, so this is one different case from any other where your potential is not depending upon the generalized velocity. The second thing is the cyclic coordinate. So we define the conjugate momenta or generalized momenta, and the second thing, important thing, is cyclic coordinate. The cyclic coordinate is nothing but if you write the Lagrangian of the system, and if the Lagrangian does not contain the coordinates, but it contains the generalized velocity, then that particular coordinate is your cyclic coordinate of that particular Lagrangian or particular system. This is also known as the cyclic, or it is ignorable coordinate. So if you write your Lagrangian, if Lagrangian generally depends upon q, q dot and t, but if your Lagrangian is not depending upon q, so q is not present there, that is the coordinate is not present there, then that coordinate, but the corresponding velocity is present in the Lagrangian, then that coordinate is known as the cyclic or ignorable constant. So if you see your Lagrange equation of motion, that is d dt of q dot and qj. So when I'm saying that Lagrangian is independent of q, so this is going to be 0 because Lagrangian doesn't depend on q. So I have d dt of delta lq is going to be constant, and I define that conjugate momenta as delta l by delta q dot j. So this is going to be the pj, the conjugate momenta is going to be constant corresponding to that cyclic coordinate. So when your Lagrangian is independent of the coordinate, but the corresponding generalized velocity is present in the Lagrangian, so the corresponding momenta of conjugate momenta corresponding to that cyclic coordinate or ignorable coordinate is going to be the constant of motion. For example, in a free particle case, when a particle is free to move anywhere, so you write the Lagrangian as half m x dot square plus y dot square plus z dot square, and then there is the potential. So when you write the Lagrangian is t minus v, this is nothing but half m x dot square plus y dot square plus z dot square. So the Lagrangian is not depending on x. So Lagrangian is not depending upon x dot t. So x is not there. It's not depending, but the corresponding velocity is there. So when the corresponding velocity is there, and so x is the generalized coordinate in case of x, y, and z, because now you have three generalized coordinate here in this case. The generalized coordinate here in this case, q1 is x, q2 is y, and q3 is z. But all these three are not present, but the corresponding velocities are generalized velocities are present. Okay, so these are x, y, and z in this case are the cyclic coordinate or ignorable coordinate, and the corresponding momenta is going to be a constant of motion. As we have already seen, the corresponding generalized momenta for that, because corresponding generalized momenta is going to be delta s by delta x dot based on this definition, because this is delta s by delta x is going to be mx dot. Okay, so you see this is mass into the velocity in the x direction, and the corresponding to that the linear momenta component of the momenta in the x direction is going to be the constant of motion. Because if you write this equation of motion for that is going to be d dt of delta l by delta x dot minus delta l by delta x is equal to 0. But this is 0 because Lagrangian is not depending upon x. So this quantity d dt of this you calculated as this is going to be mx dot equal to 0. So this is the conjugate momenta is 0 time derivative. So conjugate momenta is the conserved quantity in this case. So if your Lagrangian is independent of the coordinate, but the corresponding generalized velocity is present there, so then their corresponding, then that particular coordinate is known as the cyclic or ignorable coordinate, and corresponding to that cyclic coordinate, the momenta, the generalized momenta is going to be the constant of motions. So hence we can state that as a general conservation theorem that the generalized momenta conjugate to a cyclic coordinate is always conserved. Okay, one more case you can take that for this. If I say the Lagrangian is half m plus m r dot square plus r square theta dot square plus mg l minus r. So this, if this is my Lagrangian, so this Lagrangian is depending, there are two generalized coordinates, this is r and theta, and so it's not depending upon, the Lagrangian is not depending upon this theta. So I have theta dot and r dot is here, but there is no theta. R dot is there, r is there, theta dot is there. Okay, r is there, r dot is there, theta dot is there. So there is theta is not present there. So theta, being theta is a generalized coordinate, is not present in the Lagrangian, but the corresponding generalized velocity is present. Okay, is present. So this theta is the ignorable coordinates or cyclic coordinate, and the corresponding to that conjugate momenta. If you write the corresponding momenta, for see that if I write here somewhere that if this is my Lagrangian, if I write to the Lagrangian for that, this is going to be d theta corresponding to delta L by delta theta dot minus delta L by delta theta is going to be 0. So this is the Euler-Lagrange equation corresponding to theta, but because it's not depending upon theta, L is not depending upon theta, there is nowhere in the Lagrangian is theta is there, so this is going to be 0. So what I'm going to have is, this is d dt of delta L by delta theta dot equal to 0, or that corresponds to delta L by delta theta dot is constant. And what is delta L by delta theta dot? If you compare with the definition of the conjugate momenta, is the momenta corresponding to the theta. Okay, and what is del by del theta? So because theta is there, this is going to be, this is m plus m r squared theta dot. Okay, so this is p theta is if you write p theta here is m plus m r square theta dot. Okay, so if this m plus m is some constant, some m naught, and so this is r square theta dot. So you see that is the angular momentum. Okay, so the angular momentum is correspond, because if you see that if my q is angle, then the corresponding generalized momentum is the angular momentum. So here you see that here the theta is the cyclic coordinate, and the corresponding generalized momenta is going to be constant, and that is going to be the angular momentum. Okay, so I hope you understand the concept of what is conjugate momenta or generalized momenta and the cyclic coordinate. Conjugate momenta is simply the momenta, the quantity which is like the partial derivative of your Lagrangian with respect to the generalized velocity, and the cyclic coordinates are those coordinates which are not present in the Lagrangian, and but the corresponding velocity, generalized velocity, is present, and corresponding to that generalized momenta is going to be the conserved quantity. So now let's move further for this conservation of conserved quantity, that is linear momentum conservation and angular momentum conservation. This is based on the fact that the Lagrangian is independent of the generalized. Two things is there. The Lagrangian is having some cyclic coordinates, and your potential is independent of the generalized velocity. So for the linear momentum conservation, let us consider that the generalized coordinate is qj, and this delta qj represents the translation of the system as a whole, because when we're talking in terms of the generalized coordinate, you are in a configuration space, and in a configuration space, each and every point define the unique configuration of the system as a whole. So that means if the system is being translated from one position to the another position, so that is given by delta dqj. Okay, so earlier my system was here, and then it is transferred to here in the configuration space, and that depends upon qj, and this is delta qj. So that path is defined by dqj. This represent the translation. And suppose that the velocity are not affected by the shift in the origin. That is, if you think in terms of the Cartesian coordinate, if you shift the origin, then the center of mass velocity is not going to affect. This is going to be constant. Okay, so that was the kinetic energy, because the velocity is not going to be affected. So the kinetic energy with the translation of this generalized coordinate is going to be 0. Okay, so one thing is that, and there we assume for the conservative system. For conservative system, v is not function of the velocity, so that is the delta v upon delta q dot is also going to be 0. So one is this thing, and the second is the this potential, not velocity, sorry, velocity is independent of the potential is independent of the generalized velocity, so this is also going to be 0. So since your Lagrange equation is, you write my Lagrange equation is here, so you can see here, this is my Lagrange equation, and L is contains T and V, kinetic energy and potential energy, T and V. But the condition we put that first is that this kinetic energy is not depending, is independent, it's not changing with the translation of the generalized coordinate. So here, if you see this part, delta t by delta qj is not going to contribute, but velocity is depending upon q, so this remains same. And second, when the velocity is in potential is independent of the generalized velocity, so here delta, this is going to be 0, so I am left with only this quantity. So this is what my Euler-Lagrange equation comes to this form. Okay, so when the system is being translated in a configuration space with the condition that the kinetic energy is not changing and the potential is not depending on the generalized velocity, this is for the conservative system, is already there. So what I have is the kinetic energy is containing only this q dot generalized velocity part, and the potential energy is depending upon only the generalized coordinate. Okay, so this is what I have. This is equal to minus of del v by del q, and this del v by del q, as you know, is my generalized force, because when my system is conservative, then my conservative forces can be written in terms of the gradient of the potential, that is minus del v. And so this is already there, and we define our generalized force. We already know that this is the force applied, and the dot product of with delta ri upon delta qj. And here the delta q dqj is corresponding, so translation of the system. Dqj is translation of the system from here to here. That is, if this is, if trying to find it, that what is dqj, that I have to differentiate it from this. I'm going from this position to this position, so going from this position to this position and taking a limit going to be 0. So delta r partial differentiation at that qj point, this is how you define the translation and differential form. So this is this r dqj, this is this part is dqj, and here I have this, and then I have a unit vector with this, where this in which direction my dqj is, in which direction the direction n is giving you the direction, unit direction in which the system is being translated. Okay, so because you limit del j is equal to 0, dq dq will 1, so what I am going to have is only the n dot. So dri upon dqj is here in case of n dot. So I can put in the generalized force in place of this, as this is going to be n dot. So this is, if you sum over all the forces, going to be n dot f. So then I going to put this q here. Okay, because this has to be, remember that q is n dot f. Now you define the kinetic energy is half mi r dot square. So the conjugate momenta is delta t upon delta qj. That is the conjugate momenta, because basically when you define this conjugate momenta, pj is basically delta l by delta q dot j. But because this is delta q dot j, and this is t minus v, and we already know that v is independent of the generalized velocity, so I just have delta t by q dot j here, so that is delta t by q dot j. So that is t is my half miva square, so if I differentiate with respect to qj, so this becomes twice ri, so this is twice ri, and then ri with respect to qj, ri with respect to ri dot with respect to qj, 2 will get cancelled out, I have mr ri, and this is delta ri by delta 2. If you remember earlier that we have already set the equation that delta ri upon delta q is equal to delta r dot upon delta q dot. If you remember, if you go to the previous slide and if you see that, so this is equivalent to writing this. So, and this is nothing but, if you remember, this is nothing but my delta ri upon delta qj is the unit vector in the direction of the translation. So I can put this is n, and this is what I have. So this is the linear momentum of all the particles, and then each and every particle, if you sum over this, so finally what you are going to get from here is total momentum in the direction of the translation is going to be constant, because you have put in the condition that the qj is if the qj is cyclic, so I have d dt of delta t upon my equation is delta t upon delta q dot minus delta v upon delta q equal to 0. So if qj is cyclic, then this is going to be minus delta v upon delta q is going to be my force, as already considered this, because qj is cyclic. So okay, you see here, so this is going to be 0. So now the conjugate momenta is pg, and this comes out to be this thing. Okay, so if you remember, so now the d dt of this quantity which we have figured out, what is dt by dq, is going to be constant, and this n dot total momenta is going to be conserved quantity. So we have seen that the translation of the system in configuration space from one point to another point, and if considering that this kinetic energy is not affected by the translation, and the potential is independent of the generalized velocity, so because kinetic energy independent of that, this is q is going to be cyclic coordinates, and then with this condition you see that the total linear momenta is a conserved quantity. Okay, so I think I'll stop here, and in the next class we will go for this angular momentum conservation and the total energy conservation. These two angular momentum conservation and the total energy conservation we will cover in the next class. Okay, so this is all for today's lecture. Thank you for your patience and listening me carefully. Thank you all.